Hello and welcome to the Westcountry Rivers Trust Catchment Science Webinar Series. I'm Nick Paling and I'm Head of Evidence and Engagement at Westcountry Rivers Trust. And over the last 10 years I've been heavily involved in many of the Trust's integrated catchment management, collaborative governance and strategic catchment evidence programmes. This is the fourth and final webinar in this mini-series of 4 episodes focusing on how we have used a 5-stage proof-of-concept approach to support the delivery of South West Water's flagship environmental management programme, Upstream Thinking, over its first 10 years. In the first webinar in the series, I gave you an overview of our 5-stage approach to using data and evidence to inform the design, delivery and iterative improvement of adaptive catchment management initiatives. In this webinar, I'll be examining the 4th and 5th stages of our proof-of-concept approach in more detail. These stages focus on our approach to the monitoring and evaluation of our catchment management work, including the assessment of secondary benefits generated, and also the dissemination and influencing we've been able to undertake as a result of this work. Hopefully what you'll see in this presentation is that these stages of the process are critical as they allow us to perform effective dissemination to showcase the environmental, economic, social and cultural value generated by the scheme. They also allow us to influence environmental strategic planning and policy development locally and nationally, and they are vital in facilitating the continuous improvement of the scheme overall. During my summary of these final 2 stages of the process, I will give examples of the various studies we've undertaken and the outputs and case studies we have produced over the years. Perhaps most importantly, the presentation will include all the links you need if you would like to find out more information about any of this work. So back even before Upstream Thinking was initiated, back in 2010, we'd already spent quite a lot of time over the previous 5 years working with South West Water and other partners to examine the effect of farm advice and investment on water quality in streams. And one of the best examples we have of this is the work that we did around Upper Tama Lake, which is a drinking water reservoir with a drinking water catchment around it in the very headwaters of the Tama catchment. And we provided investment in the form of grants to a whole series of farms around that reservoir, and what we were actually able to show by monitoring invertebrates in the streams above and below the farm, we were able to show quite a rapid recovery in the invertebrate assemblages and biodiversity within those streams. And we've continued to work around Upper Tama Lake in Upstream Thinking itself in phase 1 and 2. And we've continued to look at the data and monitor water quality parameters during that time, and we've actually been able to see some emerging trends in terms of reductions and changes in, for example, nutrient levels in those streams, and we're continuing to monitor that work. And this was a very good example of a case study at a very small scale, at the scale of a single farm, but obviously this teed up the challenge of, as we went into Upstream Thinking, of looking to see whether we could detect these changes at either a subcatchment or hopefully even at some point a catchment scale. Also at that time, between 2010 and 2012, we collaborated with a number of academics and researchers, particularly from the University of East Anglia, and one academic in particular, a researcher called Toby Kruger from University of East Anglia, had developed a nutrient source apportionment model called ECM+, and we were able to use this. It was a participatory model which you ran in collaboration with farmers to look at specific scenarios, and the model would predict, based on water quality data that was used to calibrate it, the likely export of pollutants, in this case phosphorus, from either subcatchments in the Tama catchment or indeed the whole catchment. Working with farmers, we ran scenarios in the model, for example, to look at what if 100% uptake of best farming practices was delivered on a subcatchment like the Cordworthy Water, highlighted here, and you can run the model and see the shift that's achieved. So for example, scenario 2 at the top here shows that phosphorus export has gone from around 2.5 tonnes per year down, in this case, to below 1 tonne a year, but there was no change obviously at the whole catchment scale. and other scenarios looking at, what if 100% uptake of best farming practices was delivered across the entire Tamar catchment, and as you can see, no additional benefits in the Cordworthy in the subcatchment scale, but then at that level you start to see a reduction in the tonnes of phosphorus exported per year in the bottom right hand corner there, at the bottom, at the outflow of the Tamar catchment. And we used the model as an engagement tool. We used it to build rapport with stakeholders. We used it extensively during the Tamar catchment partnership pilot in 2012. Particularly it allows us to set out to understand and characterise what might be achieved under a series of different scenarios as we went into delivery of Upstream Thinking 1 and indeed Upstream Thinking 2. This is a very important tool, but it still needed to be validated with a monitoring approach as well. But it really did set out what we could aim to achieve, and was vital therefore in the proof of concept process. Subsequent to that, between 2012 and 2014, myself and colleagues worked to produce a water quality evidence review. This was a literature and case studies review presented in a very open and accessible format and language. Really focused on trying to set a benchmark for the current state of the art in integrated adaptive catchment management, particularly performing a literature review and gathering case studies to try and benchmark what might be achieved in terms of changes or improvements in water quality through a catchment management scheme such as Upstream Thinking. And this document is available online, and indeed there are some hard copies still around, although they've become very rare. But this is a very important output for us because it really did set that benchmark again in terms of establishing the current level of understanding and the current state of the art in terms of catchment management proof of concept. As Upstream Thinking began, and in a number of catchments, the advisors and specific partners began to undertake their own monitoring work to try and assess the outcomes that they were achieving through their work. And perhaps the best example is the work undertaken in the River Otter. And this catchment scheme was very focused on nitrogen, nutrients lost into the water environment from the farmed environment. During Upstream Thinking 1 and 2, around 133 farmers have been given advice and investment to try and reduce particularly the loss of pollutants, but particularly nutrients, into the water environment. And obviously the Otter catchment is quite unique in the Westcountry in having a groundwater aquifer underneath the ground as well. And we've done a full review of all of the advice and investment that's been given, and this just shows kind of the estimated outcomes that we're hoping to have achieved. And as you can see, the desk study shows that nitrogen losses to the environment are likely to have been significantly reduced as a result of the advice and investment that's been given. But indeed, the farm advisor working in the catchment also took a whole series of soil samples, nitrogen samples from 10 fields across the catchment over a 9-year period. And what they were able to show is that actually over that time there was a significant reduction in the nitrogen being lost from soil following application as fertiliser, particularly into the water environment. So this went quite a significant way to showing, using a combination of a modelling and estimating approach, and actually then verifying that with a monitoring study to actually show what was likely to have been achieved. And this was heralded as a great success in showing this significant reduction in nitrogen losses to the river. Now, our proof of concept work has particularly focused during Upstream Thinking 1 and in the early years of Upstream Thinking 2 on one specific subcatchment. And I've already seen it in this presentation, which is the Cordworthy water. By chance, during 2010 and 2011, we were working on the DEFRA Strategic Evidence and Partnership project, and this work, which was really studying collaborative working, building payments for ecosystem services schemes, building collaborations between the water company and in particular rivers trusts, local delivery organisations, happened to coincide with a Westcountry Rivers Trust hosted workshop for the DEFRA demonstration test catchment project, which was just being initiated at that time. And during that workshop, Cordworthy Water was identified. It's one water body in the Ottery subcatchment of the Tama, and it was identified as being a really prime candidate for a proof of concept study. And it was agreed between the demonstration test catchment DTC group, the DEFRA stakeholders, and ourselves that that Cordworthy Water would become a DTC study catchment, that we would deliver farm advice and integrated catchment management in the catchment, and that the researchers would monitor before and after those interventions went in order to see whether or not we could change water quality at a catchment scale. So in 2012 to 2013, the DEFRA DTC consortium monitored Cordworthy Water, and you can see the extent of the catchment. It's about 3.5 kilometres from north to south along the length of the stream, and they monitored Cordworthy, this catchment, at very high spatial and temporal resolution. They monitored soil in the catchment, they measured the biology of the river, the chemistry of the water, and indeed they monitored the hydrological flow regime in the stream as well over that 2-year period. And that was establishing effectively a baseline prior to intervention. In the following 2 years, Westcountry Rivers Trust went in with their farm advisors and engaged all 21 farms, delivering integrated farm advice to 19 of them, and ultimately delivering just under £500,000 worth of investment on 11 of the farms. The farmers contributed a further 158,000 of match funding, bringing the total investment in the catchment to just under £600,000. And we then began the process of trying to characterise what we delivered and indeed what we'd achieved in terms of change in the environment, particularly in water quality. And this graphic shows the outputs from a model called FarmScoper, which we've used to actually try and assess the likely reductions in pollution that we might have seen, or we might expect to have seen, in the catchment during following those interventions, and indeed which we were hoping to verify with the DEFRA DTC monitoring, which was ongoing at that time. So the DEFRA DTC group continued their monitoring in the 2 years after intervention, and what they started to see is actually there were some significant changes in some of the chemistry in the river at certain times. Overall, between the baseline years and the post-intervention monitoring, as you can see from this graphic, there was a general reduction, for example, in nitrogen concentration, but actually further investigation revealed that many of our rivers in the Westcountry have also exhibited this reduction in nitrogen pollution. However, the Cordworthy Water did show a fairly stable water quality situation in regard to many other parameters. And what we also found in our further investigations was that many other streams in this part of the southwest landscape have actually seen significant deterioration over a similar time. So it's a very complex situation, but we've started to see some significant changes as a result of the interventions that we've delivered, or that we think have resulted from those interventions. And on the right here, what you can see is that actually we've seen a shift in the nitrogen, the types of nitrogen chemicals, compounds which are occurring in the Cordworthy Water. So not only is there less, but actually we're seeing a shift in the composition of the nitrogen, seeing reductions, for example, in nitrogen associated with slurry and other sources. So again, indicative, perhaps showing the first signs that we may have shifted the pollution dynamics of the catchment landscape by delivering catchment management advice and investment. So by no means definitive, but certainly interesting preliminary signs in the data that we gathered through this project. So in addition, the DTC group also undertook extensive biological monitoring pre and post intervention. And this graphic here shows what they found. And what it shows is that in the Cordworthy catchment, there have been significant increases in a number of biological metrics, in particular relating to invertebrate abundance, and particularly certain types of invertebrate species showing a greater abundance in the stream. And this is indicative of improvements in water quality. And it's interesting to note that the control catchment, which is across the watershed in the Neat and Strat catchment, has actually during the same time seen a significant deterioration in these indicators, as you can see in the top right corner. There have also been some early indications that the fish populations in the Cordworthy water have improved following our interventions, and overall there's been a number of shifts in invertebrate indices observed across the Tama catchment more widely as a result, or during the Upstream Thinking delivery phases over the last 10 years, and we're still doing more investigation to see if we can connect those changes in the biology of the river to the interventions that we've delivered. So another tool that we've used to try and characterise the likely improvements that we might be achieving in terms of water quality outcomes is that we've developed a pesticide simulator, and this is the subject of another webinar in this series where I go into a lot more detail about the workings of the pesticide simulator and certainly what we've learnt through the process of developing it. But suffice to say, just to signpost to it now so that you're aware that it exists. So the Upstream Thinking Pesticide Pollution Simulator, we undertook a review over 5 years of all the existing pesticide models, and we identified that what we really needed for the Westcountry catchments that we were working in didn't really exist. We in fact identified that what we needed was a simulator that allowed us to assess the risk of pesticide pollution at a very fine spatial scale and also at a very fine temporal scale. We wanted a tool that incorporated local data and local information, and we wanted a tool that helped us target, design advice and measures for pesticide control, if you like, in terms of water quality problems. We also wanted a tool that would be able to simulate stochastic pesticide pollution events and characterise the very rapid fluxes that we saw in particularly acid herbicides in our grassland dominated Westcountry catchments. So it needed to work for grassland dominated catchments, and we wanted to be able to use the simulator to demonstrate the likely changes in pesticide pollution events, both frequency and magnitude, that might result from the land management advice and measures that we were delivering in Upstream Thinking 2. So we built the simulator, and again I go into much greater detail in the pesticide simulator presentation. The simulator allows us to model flow as a result of rainfall in any particular catchment and soil hydrology, and it then simulates a profile of pollution events, in this case over the course of a year for MCPA, but we developed it for a whole series of different acid herbicides. And then we were able to compare to some degree what the simulator predicted with the South West Water pesticide detections, which they have been monitoring under their statutory monitoring programme on a monthly basis in a catchment like the Tama over many years. And there's quite high correspondence between the simulator and what it predicts, and obviously the detections database, and we're looking at that in more detail as we speak. But the key thing with the simulator is it allows us to look at different scenarios, things that we might advise farmers to do, changes in behaviour, changes in practice, and to see how we think the simulator thinks they will affect these advice and investments will affect the dynamics of pesticide pollution in the catchment. So one example that I've shown here is if you shift active ingredient use onto permanent pasture in the autumn and change the emphasis to spring rather than winter cereals, for example, what effect does that have? And so on this graphic you can see the baseline and then the scenario, and what it shows is that actually the frequency and magnitude of events in the autumn has increased as a result. And actually in the autumn, because of this shift in permanent pasture acid herbicide use to the autumn, we actually see a much greater number of significant pesticide pollution events. And so again, this just illustrates the way that we can use the simulator to learn about the way that pesticides are both used and the way that we might change their loss, the dynamics of their loss to the water environment. So in terms of the other thing we've been looking at in great detail, is the dynamics of the way that secondary or multiple benefits are realised as a result of our upstream thinking delivery. Obviously our primary driver is to improve water quality, but there's always been an expectation that our interventions would deliver other outcomes as well. And so we have been developing a programme of monitoring and evaluation to look at the accumulation, if you like, of these other secondary benefits. So between 2016 and 18, we started to get numerous anecdotal reports of ecological recovery in the Ottery and Upper Tama catchments and various other places. And the data here is actually catch returns data for fishing beat on the River Ottery. And it's anecdotal data, it's anecdotal information, catch returns, but there's a clear trend that suggests to us that the fishery is improving in terms of, in this case, number of fish caught. So in 2017-18 we initiated a secondary project to Upstream Thinking, Proofofconcept, which we called Biodiversity Byproducts, which was a study undertaken with the University of Reading to examine the changes in biodiversity realised through the delivery of Upstream Thinking measures. And that work is ongoing, and it's become very important in Upstream Thinking 3, which has a much greater emphasis focused on biodiversity outcomes in Upstream Thinking anyway. Between 2015 and 2018, and in fact for many years before that, we've had a significant interest in soil research, and we've collaborated with a whole raft of partners and stakeholders and worked on a number of projects looking at soil health, soil organic carbon content, particularly in relation to Upstream Thinking delivery, and that research is continuing via a number of projects and initiatives to this day, and it's becoming increasingly important that we are able to evaluate carbon sequestration in soils particularly, and also the relationship between soil health and ecosystem service provision in a great many of our catchments. So that work is also ongoing. This graphic is just to remind me to mention, of course, Upstream Thinking is a natural capital approach, and we've been doing a huge amount of research through DEFRA-funded projects, Environment Agency funded projects, and European funded projects to look at ecosystem services and natural capital assessments, and particularly making those assessments in a collaborative and participatory way. And this graphic is showing ecosystem service provision by soil in this case, but also connecting that through to likely benefits that soil provides when it's healthy and functioning correctly. And we use these devices to help build a narrative about value, and indeed potentially to also develop valuation techniques in relation to natural capital assets. So we have these kinds of graphics and with data and metrics sitting behind them for all of the natural capital assets in both urban and rural landscapes, and we're now working to develop this kind of approach in Upstream Thinking 3, which where there's a real emphasis on natural capital approach in the assessment of benefits being realised through the delivery of the scheme. So the final case study that I wanted to look at is that during the development of Upstream Thinking 2, and again during the development of Upstream Thinking 3 in 2013 and 2019 respectively, we have been working with South West Water to try and get a handle on the mechanisms and the processes via which upstream thinking catchment management could effectively deliver cost savings for South West Water in the drinking water treatment process. You may remember in presentation 1, in webinar 1 in this series, that one of the original fundamental challenges of upstream thinking was that it was primarily designed to make South West Water's drinking water treatment processes more resilient, to essentially save them money and investment requirements in their drinking water supply chain, to ultimately make it more resilient. So this graphic shows that essentially the process that South West Water go through in their drinking water treatment process. They take polluted water, they clean it and prepare it for drinking water provision, and they remove pollutants from it. And we are able to determine from South West Water data what that process costs per litre, and we're also able to determine the processes and decisions that South West Water make as they go through that process, and the effect that that has on that cost. So some costs are fixed, some costs are variable, and it's very much the variable cost that we're interested in relation to upstream thinking, because upstream thinking catchment management in theory could reduce the variability of costs as they're incurred. So a lot of our work has been looking at the pollutants that are in the raw water before it's treated and provided as drinking water, and obviously a huge amount of work has been done trying to work out where those pollutants come from in the catchment, because if we can work out where they're coming from, then we can work to reduce their losses into the water environment and hence into the raw water. Some pollutants in water are natural, however many aren't, and the ones that aren't can potentially be reduced. And of course the other thing that we have to try and understand is the risk associated with this process. But there is always a risk that treatment failure leaves pollutants in the final water. That is a major issue for South West Water, and potentially it's an issue for their customers, and we can potentially mitigate that risk by delivering catchment management processes. And so we spent quite a lot of time working with South West Water to study all of these different processes and the way they interact. And indeed we were commissioned by South West Water to undertake a study to test scenarios of how catchment management could actually realise cost savings, and really go through a process trying to elucidate what success in catchment management actually looks like from the perspective of South West Water and their business. So we did quite a lot of work examining the effect of changing the way that benefits are accumulated after catchment management interventions. And also we were trying to work out whether or not more cost savings would result from low impact, long lasting interventions or very high impact, short term measures. And so looking at trade-offs between different mechanisms of delivering the upstream thinking scheme. And in order to examine this in more detail, we essentially developed a very simple model looking at the changes in annual cost of treatment, water treatment works, and that's shown here. And then we ran simulations, scenarios, to look at the way that cost savings would manifest at the water treatment works by using that simulator. So we were able to look, for example, in the top graph, this is where there's a very rapid degradation of benefits after investment, so with a 5% reduction realised each year, but they're lost very quickly. And the difference in the lower graph between that and 5% reduction realised each year, but with a very slow degradation, or indeed interventions delivered to maintain those benefits over a longer period. And that makes a difference of, for the same investment, the difference between 0.7 million of total accumulated cost saves and 1.2 million. So being able to use a simulator like this to conceptually try and understand how catchment management connects through to deliver cost savings to South West Water has been really interesting, and this work is also ongoing at the moment. And there is a report available about this work, and this will be the subject of another webinar in this series. So if you're interested in this kind of thing, then look out for that. Okay, so that's the end of this fourth and final webinar in the series, which has focused on our approach to the monitoring and evaluation of our catchment management work, including the assessment of secondary benefits generated. We've explored how this feeds into the dissemination and influencing we've been able to undertake as a result of that evaluation work. I hope you found this presentation useful and interesting, and indeed the whole series. Please note that all of the outputs I've summarised can be found via links in the supporting information provided alongside it on the WRT Catchment Science video channel. Thanks for watching this Catchment Science webinar. More webinars will be released on this channel over the coming weeks and months, so watch this space, and I hope that you'll be able to join me again for some of those.